Good morning, Mr. Herman here. This is our first Ed Puzzle video of the year. What we'll be doing throughout the year is we will have Ed Puzzle videos through all of our major topics that we're covering throughout the school year. So you can go back and watch these videos, and throughout the videos we'll have some questions that you'll be answering as a homework grade in the Ed Puzzle video. So, for our first lesson, we're going to do some review of transformations and talk about dilations. So we saw dilations a bit before in class earlier this week. However, we're going to go ahead and try to bring it down to the nitty-gritty of what are we actually doing. Okay, so we're going to go ahead and review our transformations first. So last year in Integrated Math 1, you should have seen these three transformations. You might have seen them before Math 1, but we'll go through these right now. So in our first figure, we have two triangles that are sliding across a grid, a coordinate plane, and we're going to call it a translation. Okay, I'll put slide underneath it in case you're more familiar with that language. Now this one, it's kind of hard to see on the video here, but we have this low point of our triangle going to the other side of the y-axis, kind of like a mirror. And so if we see that mirror image, we have a reflection. Okay, you might also know this as a flip. And then this last one here, we've got the flat end of the triangle rotating 90 degrees down over here. And so that's going to be a rotation. And that is also known as a turn. So these transformations, as we saw last year, and as we can see here, have the same size and the same shape. Okay. So these transformations have the same size and the same shape. And what do we call that? We call that rigid motions. Okay, the size stays the same and the shape stays the same. Now, what we've been looking at this week is we've seen that the shape stays the same, but the size doesn't always stay the same. Okay. Now, if the size and shape do not stay the same, we call those non-rigid. Okay, those are non-rigid motions. So this means that the shape and or size changes. Okay, so one of those has to change, or both can change. Okay, so we've seen that this week when we've been talking about dilations. All right, so we've got a nice little picture of a dilation here for us. Okay, we have our center of dilation here. That's our important point. And then we have two figures here, two triangles. And so let's look at some key features, some properties of our dilations. Okay. So in our dilations, our sides are going to be something that we call proportional. So proportional means that there is a common ratio or a scale factor between the two pairs of sides. We're used to seeing congruent. Okay, so we're not going to have congruent sides in dilations. Our corresponding angles, so that's the angles that line up, so like A and D are angles that line up. Those are going to be, so you have the one mark here and the one mark here. Those corresponding angles are congruent. So our sides are not congruent. They're proportional, but our angles are congruent. And so if our sides are not congruent, but our angles are congruent, we know that the figures are not congruent to each other. Okay, we need both congruent sides and congruent angles. And then if you notice here, the lines connecting the corresponding angles all meet at a point. So we have D and A. This dashed line goes to here. F and C goes to here. E and B goes to here. So the lines connecting the corresponding angles all meet at the center of dilation. Okay, that is a C. All right, so we've kind of seen what that dilation looks like. All right, so let's go ahead and look at one other property of dilations that we talked about this week, and that has to do with the idea of our scale factor. Okay, so I'll flip over our page real quick. So the proportion, we talked about proportional size, the proportion between side lengths in the dilation is called the scale factor. Okay, so we talked about the other day, if k is greater than 1, okay, see, I'll put a little word down here. We want to think of it as the multiplier. Okay, so if we're multiplying by k, that's the letter we use to show the scale factor typically. If we multiply by a number bigger than 1, the image gets bigger. Okay. If we multiply by a number less than 1, the image gets smaller. And then if k equals 1, if we multiply by 1, the image stays the same. So when we're looking to identify scale factors, sometimes we'll be told a scale factor, but other times we have to find a scale factor. We have to use our formula of image over pre-image. Okay, so we'll do a quick tangent here to remind ourselves of image and pre-image. So if you know image and pre-image, you don't need to write this down. The pre-image is where you start. The image is where you finish. So where are we at the end? So that dilation we looked at the beginning, we have to check our scale factor. Okay, so we're going to take a look back at it. So you might want to flip over. We're going to just look at the screen here. All right, so we said that the pre-image is ABC, is triangle ABC. So we start at ABC. Okay, so what I want to do is I want to take one of my sides, AC, that's 8, and we know pre-image goes on the bottom of the fraction. So what corresponds with AC is going to be DF. Okay, so what I'm going to do is I'm going to show that K equals DF over AC, which is the same as 16 over 8. And that equals 2. So there's our scale factor. So I can check each one to make sure. So BC and EF, 8 divided by 4 is 2. So that's good. And then AB and DE, 12 divided by 6 is also 2. So my scale factor should be the same for every pair of sides. Now, if we went backwards and said that triangle DEF is the pre-image, we start at the big triangle and we go to the small triangle. Let's go ahead and do K. The only change is that I now have AC over DF. So 8 over 16 is 1/2. So if I'm going backwards, that means that my scale factor is the opposite. So I have 2, and then that would go to 1 over 2 if I go the other way. Okay, so hopefully that makes a bit of sense. If I go one way, it's 2. If I go the other way, it's 1/2, because I'm multiplying here. So 2 times 1/2 gives me 1. So now we're going to go ahead and perform a dilation here. Okay, so construct a dilation of triangle QPR with center of dilation at 0, 0 and k equals 1/2. So before we begin our dilation, do you think your image will be bigger than, smaller than, or equal to the pre-image, and why? So hopefully you said it will be smaller. So smaller because k equals 1/2, and that's less than 1. Okay, because our scale factor multiplies. If I multiply by a number smaller than 1, my outcome, my product, is going to be less. It's going to be smaller as well. So let's go ahead and do our dilation here. So let's point out where our center of dilation is, 0, 0. So in order to get to point, let's start with point R. So R, I'm going to go 1, 2, 3, 4, 5 in the x direction, or I'm going to go x comma y up to, and then I need to transform it. So I'm going to say times 1/2 in R prime. That's how I read that, R prime. That's where I move the point, is 5 times 1/2. So that's 2.5, and 2 times 1/2, which is 1. So we go ahead and graph that point. So there's 2.5, comma 1. Okay, let's go ahead and do our next point. Let's do Q next. So Q is 1, 2, 3, 1, 2, 3, 4, 5. So 3 comma 5 times 1/2. And then we have Q prime. So 3 times 1/2 is 1.5. 5 times 1/2 is 2.5. And let's go ahead and graph that. So I go 1.5 up 1, 2.5. So kind of in the middle of that square right there. Oh, and we should label those points. So Q prime, R prime. Now we're going to finish it off with point P. So point P is all the way at 1, 2, 3, 4, 5, 6, 7, comma 1, 2, 3, 4, 5, 6. Our scale factor is still times 1/2. So P prime, since I moved it, 7 times 1/2 is going to be 3.5. 6 times 1/2 is going to be 3. So let's go 1, 2, 3.5, 1, 2, 3. P prime. Now, we don't just want to have the points there, we want to make sure we connect the dots. Finish her up. Now we look back at our prediction. We said we predicted to be smaller because k equals 1/2 is less than 1. Our prediction is correct. And this is going to be about half the size of this triangle here because our scale factor is 1/2. Okay, all the sides are half the size. So go ahead and finish answering our check your understanding questions before you finish up this video.